I'm going to be working on a Debian Linux running on an AMD 64 processor, also known as x86-64, and sometimes just called 64-bit Intel. Because I'm working with Debian, I'll use apt to install programs. Use the appropriate program or package manager for your platform. To build programs, we're going to need the build tools, and on my platform we install those with sudo apt install build essential. It's already at the newest version, so we're fine. To assemble, we'll use the net-wide assembler NASM. Install it the same way. We'll start with a simple Hello World program. I'll use Vim in these videos, but you're welcome to use Pico or something like Visual Studio Code if you like. Any text editor should be fine. Our file is called hello.asm. Go ahead and pause the video and enter the file yourself, or just copy it from the description. Be sure you've installed both the build tools and NASM as described earlier, and then you can follow along if you'd like. So now we're going to assemble this file with NASM. We're going to tell NASM we want a 64-bit ELF file as output. So -f is our file type, and that file type is 64-bit ELF. There's our input file. And by default, NASM will create a file that has a file name with a .o on the end, but if you'd like to be specific about that, you can give the output file like that. So it assembles without any errors or warnings. But what if we had some errors? Well, let's introduce a few and see what happens. So let's go ahead and misspell section. Let's take that colon off. Let's add some gibberish here. There we go. That looks pretty good. Let's go with that. So let's try to assemble it again. Look at that. So we have errors on line 2, line 4, and line 10. On 2, it says, hey, I expected an instruction and I didn't see one. On 4, it says, I saw what I think is a label on a line without a colon, and that might be an error, and then the same thing on line 10. 2, 4, and 10. Well, here's line 2, and if we look at that, we can see, oh, sure enough, we misspelled section. 4 is right here, and that's missing a colon. And 10's down here, and it looks like all the others, but it's not something that the tool recognizes. Let's get rid of that. Now we're back to assembling without any warnings or errors. I encourage you to play with this a bit so you recognize problems later on. Now, even though hello.o is a binary file, it isn't an executable file. To make it executable, we have to link it, and that's the job of the linker. And on Linux, that's named LD. So we give it all the .o files that will make up our program, and in this case, there's just one. And we do have to specify the output here. So we'll say -o hello. If you don't specify the output, you'll get a file called a.out, which probably isn't what you want, and it's confusing in that it isn't even in the a.out format. Don't worry about what linking means right now. We'll discuss it as we go along. We link without any warnings or errors. So with all this done, we can now run our code. And there we go. Hello, assembly world. Now, notice the leading / right here. This is to help the shell find the executable, since the current directory isn't in the search path, and that's correct. Putting the current working directory in your search path is a bad idea. From a security perspective, it's just a bad idea. Another thing you should get used to is looking at the exit value. Every program produces an exit value, and this is the same as returning an int from your C program's main. The exit value of a process is a 32-bit integer, but for programs run from the prompt and, for historical reasons, only the low 8 bits are available to you at the shell, so you should treat this as a value in the range 0 to 255. To see the exit value of the last command, type echo $? So the last command executed, our hello, returned a 0. Let's go through the program line by line. The first line is a comment. In NASM, comments start with a semicolon and they extend to the end of the line indicated by a line feed character. NASM doesn't have multi-line comments. It only has semicolon comments. You can create multi-line comments with macros, but don't worry about that for now. You may see some NASM code that uses the hash mark as a comment character. That can sometimes work, but it's a quirk and not something that you should do. Avoid it. Just use a semicolon. The section directive is used to divide a program into parts. You can have as many sections as you want. Sections have common permissions, and some well-known sections have specified defaults. For instance, this is the .text section. That normally holds the program text, that is, executable instructions. By default, it's executable and not writable. Down below, we see the .data section. This holds initialized data, that is, data whose value is specified and normally fixed. By default, it's not executable. Further down, we see a section named .note.gnu-stack, and this section has no content. There's nothing after it. It's just here to serve as a marker. The linker will see that this section is present, and this will tell the linker how to define the stack for the program. In this case, we want the stack to be not executable, and that's what you want from a security perspective. You want not executable stack. In some rare cases, you might sometimes want executable stack. That will give you executable stack, but typically you're going to want non-executable stack. In fact, if this line weren't here, you could omit it and it would be fine, but it's a good idea to get used to being specific about this. If you're very curious about why someone would want executable stack, look up nested functions and stack trampolines. You can name sections whatever you want. For instance, we can change the name of .text up here to, let's say, Fred. Now, the dot in front of standard section names is just a convention, and it's not required. And one nice thing about having the dot in front of the standard section names is we know that Fred won't collide with any standard section names. If we change this to Fred, the assembler is not going to know what permissions to give this section. So we'll have to tell it, we'll have to fill that out. But what if we just don't? Let's try it as is. So we'll hop out of that, and we'll try to assemble it. And it assembles without warning or error. And we'll try to link it. And it links without warning or error. And in fact, we now have an executable program called hello. Let's run it. This is something I want you to get used to. No errors from the assembler or linker, and nothing works. This happens sometimes. Most errors in assembly are going to result in a seg fault. And don't be afraid of that. It's going to happen. To fix the problem, we could change the name back to .text, or we can be stubborn and we can leave it as Fred, but we'll need to tell it what permissions to use. So the first thing we want to add here is prog bits. This tells it that this section should be part of the program. We want it to be executable, so let's say exec. We don't want it to be writable, so let's say no write. And we do want to be sure the linker assigns some memory for it, so we'll say alloc. The NASM documentation covers all this when it's discussing sections. Of course, you could just use well-known section names and you won't have to bother with this. But you should be aware that it's possible that the text section of a program won't be named text. Okay? And that could be for lots of reasons. Maybe they're using an odd compiler that does something a little different, or maybe it's a piece of malicious code where someone is trying to throw you off. All right? Section names are arbitrary and by convention. Now we can assemble and link again, and it works just fine. So let's continue going through the program. The next line is global _ start. In C, functions and variables declared in a module, that is a single file, are public by default, and you can reference them from elsewhere using extern or by including a prototype. In Rust, in contrast, functions and variables are private. You have to use pub in front of them to make them public. In NASM, symbols are private by default. To make them public, that is, to allow them to be used from outside of the current file, you declare them global. In this case, we're declaring a label to be global, and that is a special label _start. And the very next line declares the _start symbol. By convention, this is the entry point of your program. This is where the first instruction is going to be found. Now, you can name it something else, provided you tell the linker what name you're using, either with a linker script or with a command line option. And we won't worry about that here. Again, I just want you to be aware that that's something that you can do. If there's not an _start in a program, don't panic. They may have just called it something else. You can think of labels as named constants. In this case, the label _start holds the address of the next instruction after the colon, which is right here. And that's move rex, 1. And this is the first assembly instruction. Assembly instructions consist of two parts: an operation, specified by what we call a mnemonic, in this case MOV, pronounced move, and operands. In this case, there's just two, rex and 1, also separated by a comma. Move is the most common instruction on the AMD 64 platform. It stores values in registers or in memory. It can copy values from registers to memory or from memory to registers. It's very, very useful. A register, like RAX here, is a bit of named storage inside the processor. You can think of the processor as having a series of little boxes, and one of them is labeled RAX. Don't confuse them with variables from your program. You don't allocate registers, you just use them, right? There's one register on the processor called RAX. It's a shared resource in your program. They have fixed names like RAX. Different processors have different names. For example, on the AMD 64, you have RAX, RBX, RCX, RDX, RDI, RSI, R8, R9, so on. On ARM, you might have X0, X1, X2, X3, or you might have the 32-bit versions, W0, W1, W2, etc. Different processors will have different names. The instruction move does just what it says. In this case, it's going to move the value 1 into the register RAX. And you can think of this, the order, as being the same as the order you would use for assignment. Move RAX, 1 moves a 1 into RAX. AMD 64 is very consistent about this. It's destination, source. It's not true on all processors. And it's not always the same across every instruction on a processor, right? For example, if we look at ARM later on, we'll notice that there are some times when it's a little different. A register has no notion of signed or unsigned, or any type information. It's just a collection of bits. I could use a 64-bit register like RAX to hold a number, or to hold 8 bytes, or just to hold whatever I want, right? It could be part of something else, right? It's just a bag of bits. The next line sets the contents of register RDI to 1. The next line is a little different. So a different mnemonic, LEA, and that stands for Load Effective Address. Now, over here we have some square brackets. Square brackets are used for memory addressing using a scale index base offset calculation that we'll cover later on. In this case, we just see a label in the square brackets. This instruction is going to store the address for the label MSG in RSI. It's just going to do the memory address calculation that we see here, and it's a very simple one. It just says what address is MSG. It's going to do that, and it's going to store that address in RSI. It's not going to access memory. There's no memory access taking place here. The next instruction stores message.len in register RDX. And you may wonder, what is message.len? Well, down at the bottom, we see message, and we also see this .len. This line uses a feature of NASM that I wish more assemblers had, called local labels. When a label starts with a period, it's appended to the nearest regular label above, in this case, message. So this gives a new label, message.len, that we see up there in that move instruction. The EQU directive sets the value of that label. So you could think of EQU as equals. So message.len equals $ minus message. The $ represents the current location in the file, the current offset into the file. So in this case, it's the first location after the end of the string. Message is the address or the offset to that capital H. And then the $ is the first thing after it. So if I take the first offset after the end of the string and I subtract the offset to the start of the string, I get the length of the string. So sure enough, message.len is set to the length of the string. So let's take stock. I stored a 1 in RAX, I stored a 1 in RDI, I stored the address to our string in RSI, and I stored the length of the string in RDX. And next, we use another operation, syscall. Before we go too much further, let's take a look at a blog post by Ryan Chapman, and you can find it at the URL you see above. The Linux kernel provides services to programs. If a program wants to do I/O, then it needs to talk to the kernel, since on Linux, only programs in ring 0 can perform I/O. User-space programs communicate with the kernel using syscall. To use syscall, you put arguments in specific registers and then invoke the syscall instruction. That's how it's done on the AMD64. The process is different on 32-bit Linux and on ARM, but you still use the equivalent of syscall. So on 32-bit x86, it's int80. On ARM 64, it's SVC0. And of course, you use different registers. So let's look in this table here. There's a table in here of all the system calls. And here they are. So what's our system call? Well, let's go back to our program for a moment. And we see that we've set RAX to 1, RDI to 1, RSI to the message, RDX to the length. RAX, it turns out, is going to select the system call. Let's hop over here. RAX1 means this is the system call we care about. Right. We're going to use this to write out the hello world string. And up at the top here we see the registers. So we set RDI to 1, that's the file descriptor, file descriptor 1 is standard out, 0 is standard input, 2 is standard error, by convention. We set RSI to the address of message. That's a pointer to our string. We set RDX to message.len. That's the number of bytes to write. And so we're all set up. Invoking syscall transfers control from user space to kernel space. It basically transfers control to the kernel. And then the kernel performs the write, and then it transfers control back to the program. Next, we set RAX to 60 and RDI to 0, and then do a syscall. And by now you know what to do, right? We know RAX 60. We know to go and look up 60 in here. And let's see what that is. There it is. It is sysexit, and RDI holds the error code, or the return value from the program. So this tells us that we're going to exit the program with exit value 0. So this syscall will happen, and it will never return. This is the end of our program. When Linux terminates our process, it removes it from the scheduler, it closes any open files, and it deallocates our memory. The return value is passed back to the caller. In this case, it would likely be the shell prompt. And we can look at it with echo $? So but following this last instruction, from which we never return, we actually have another instruction, halt. The syscall should never return because the program exited. If it did return, that would be a problem. The halt instruction halts the processor by putting it in a low power state and waiting for an external interrupt. That's a pretty drastic thing to do to the processor, and as a result, it's a privileged instruction. Okay, let's try to use it. We'll create a file called halt.asm, put the instruction in it, and we're good. So let's go ahead and try to assemble it and link it. By now you know we use ELF64 as the file format. So our output goes into halt.o, and our input is halt.asm. No warnings or errors. Now let's link it. Now we get a warning. Warning, can't find the entry symbol _start, right? We never defined _start. So in this case it says, I'm going to default to the first instruction that I see. And that's okay because we only have one instruction. The first instruction is the only instruction. That's what we want it to do. Let's go ahead and halt the processor and see what happens. And what happens is we're not allowed to do it. We see a seg fault. When we run halt, we get a processor exception because we're trying to run a privileged instruction from user space, and that processor instruction bubbles back up to us as a seg fault. If somehow that syscall did return because of unforeseen circumstances, some strange thing, running out of memory, an error on the stack, who knows, it would plow right ahead in the next instruction, which could be anything. It could be other code, it could be a data section, who knows what it would be. And the program could do anything. So having the halt there means that we will fail fast. If something goes wrong and that syscall returns, we will immediately generate a seg fault and stop the program. And that's a good way to do it. That's defensive programming. We've been talking about the string, but let's actually take a look at it. The DB is not an instruction, but a directive. This tells NASM to allocate data bytes. So DB is for data byte. And likewise, there's a data word, a data double word, and a data quad word, which allocate larger and larger chunks of storage. A data byte can be specified either by a string of characters or by numbers, like the 10 that's at the end, and you can see they're separated by commas. Now, NASM doesn't support escape characters in strings. Some assemblers do. GNU assembler does, but NASM doesn't. So if I want a new line at the end of my string, and I do, I need to put the equivalent of the ASCII new line at the end, and that's 10. So this DB directive allocates a string, hello assembly world, period, followed by a new line.